All right, let's look at a couple more examples of improper integrals, which essentially, again, just means that we have an infinity, right, and one of the bounds, either upper or lower bound for these questions. We looked at area last time, so let's jump right into the calculus for these first two, and we'll look at an application problem in the third one. All right, so we have that infinity. We switched this to a limit as b goes to infinity. And I'll elaborate on that here in a second. 1 to b, and to evaluate the integral of 1 over x to the 3, we write x to the negative 3 dx. Okay, integral of x to the negative 3 is x to the negative 2 over negative 2 from 1 to b, and we're taking that limit as b approaches infinity. So now make our substitutions. So x to the negative 2, we could factor out, again, we could factor out that negative 2 in the denominator, right? 1/2, negative 1/2. Limit b goes to infinity of 1 over b squared, because remember x to the negative 2 means that, right? So 1 over b squared minus 1 over 1 squared, and limit as b goes to infinity, so we're dividing by an infinitely large number here, right? The rule says this goes to 0. And so we just have negative 1. 0 minus 1 is negative 1, multiplied by that negative 1/2, so we get positive 1/2. All right, really quick, why are we making this substitution with b and, taking the limit? Notice if this b, if I never did that and I kept it infinity, at this point here, I'd have 1 over infinity squared. And it's like, what do you do with that, right? And now, if this is a limit as we approach infinity, kind of makes a bit more sense. Limit is that cheap way of getting around things that don't quite make sense intuitively. All right, second example. You may see some integrals that need to be by parts. This one looks like substitution is going to work. Always try u substitution, right? I see this u is ln x, and therefore du, the derivative of ln, is 1 over x. It's du over u, right? dx. And that works great because I have 1 over x dx, right? So there's our du. And then this ln is u. So rewriting that, I would have u in the denominator, and then everything else becomes du. Okay, and still 2 to infinity. Now, I wrote 2 to infinity, and we'll look at why here in a second, actually. I don't prefer to change those bounds in these types of problems. Sometimes it works out, sometimes it doesn't. But let's move forward without changing these, right? Because these are in terms of x, and I have in terms of u here, so it kind of doesn't make sense. But let's proceed as we normally do. So 2 to b, and u to the negative 1 du. And remember that I didn't have to rewrite this. In fact, I probably should have left it like this. But this is a great point to bring up. U to the negative 1, the integral, we can't add 1 and divide, right? Because that'd have u to the 0 over 0. So something's weird. So all in all, I could have left it like that, because the integral of du over u, like we're just talking about, the derivative of ln is 1 dx over x, right? And derivative of ln u is du over u, so therefore this here is ln u. Limit as b goes to infinity from 2 to b. Okay. Now, remember these here, the bounds were in terms of x, and I have a u here. So if I never change those bounds, I got to go back and resubstitute this u was ln x. So this one looks quite weird because now I have ln of x. 2 to b, limit as b goes to infinity. My limit, lim, really starts to look like a doctor's signature, but that definitely, its limit. Okay, now I'm back in terms of x. Now we could proceed. So substituting limit b goes to infinity, ln of b minus ln of 2. So in the long run, ultimately it didn't matter, because if b is approaching infinity, natural log of infinity is going to infinity, and then I'm doing natural log of another infinity, so it is infinity again. This gives me some number, I don't know, I need a calculator, but it doesn't matter. Overall, I'm getting infinity minus some small number here. This is divergent. Okay, and we had to do the calculus here because I have no idea what that graph looks like, right? But apparently from 2 to infinity, it increases without bound, so the area under that curve is infinite. All right, now let's go back really quick. I said I would talk about this whole change in bounds thing. Okay, right here, u is ln x, du is 1 over x dx. So if u is ln x, and I'm going to change these bounds here, then if x were 2, if x is 2, then u is ln 2, right? And if x is infinity, then u would be ln infinity. So that changes at this point. If I'm in terms of u right here, right, my bounds now would not be 2 and b, they would be ln 2 and ln infinity. Okay, let's squeeze a different color in here. So let's assume those ln 2 and ln infinity. Well, I know ln infinity is another infinity, right? So I would still need to make this substitution of b and still proceed here. But if you look at that, just look in ln infinity, ln 2, if I were to make that substitution, here it is here. If we had changed those bounds, what it did is it kind of saved me this step here of going from 2 to b or changing back to x's, right? And I'd have ln 2, and then I'd have ln infinity, which again we change to a b, and b goes to infinity. So it works out the same. Okay, I don't prefer to do too much substitutions in these. It starts to kind of get complex, but you can. Okay, this totally would work. All right, so we're going to end with this word problem here. Find the capital value of an asset that generates income at the rate of $5,000 per year, assuming an interest rate of 10%. This formula is given. Capital value equals this unbounded integral 0 to infinity, an improper integral, k of t, e to the negative rt dt. T is our variable of integration. It remains a t. K of t is the income. So in this example, 5,000 per year. Okay, that's the income, 5,000. This can be a function. Okay. There's another example in the textbook about getting paid for using a site for drilling gas or something like that. Well, over time, right, that oil or gas, whatever you're drilling, is going to diminish some. So it would not be a constant of 5,000 per year. It might be a function that slowly tends to 0 as the minerals are all drilled out. Okay. R, we have the interest rate here, 10%, so we change it to a 0.1. Okay, and really quick, like, what the heck is capital value? So the book gives a definition. The capital value of an asset, such as a machine, is sometimes defined as the present value of all future net earnings. Okay, so what is this thing going to net you over a lifetime? So some assets may last indefinitely, others maybe not. So that's what's going on here. So in this case, capital value, 0 to infinity. Again, we don't have a function for pt, it's just a constant, 5,000. E to the negative 0.1t dt. Okay, I could remove this 5,000, and also we need to change it to a limit. Oops. I just said I was going to factor that out. Limit. Okay. Change it to a b. Limit as b goes to infinity. Let's integrate e to the negative 0.1t. So remember, e to the kt is e to the kt divided by your k. Or use u substitution. It works. That's the whole reason we divide. Okay, let's factor out that negative 0.1. So 5,000 over negative 0.1. Limit b goes to infinity. E to the negative 0.1b minus e to the 0, right? Negative 0.1 times 0, which we know e to the 0 is just 1. But this e to the negative 0.1b, what does that mean? That means 1 over e to the 0.1b. And remember, we're doing the limit as b goes to infinity. So this is going to divide by e to some infinitely large exponent, and which makes the whole denominator infinitely large, right? So if I have 1 divided by something infinitely large, then again, that's going to tend to 0. All right, so all we have in this parentheses is a negative 1, which then we have 5,000 divided by positive 0.1, since we multiplied by a negative, which equates to 50,000. Okay, so the capital value of this scenario is going to be $50,000.